You might have heard of the Schrodinger's cat experiment. It is a reaction to the fact that quantum theory allows particles to be in two places at once, or moving in two directions at once, as long as there is no measurement taking place. Schrodinger's thought experiment involved placing a cat in a sealed box with a flask of poisonous gas. The flask can be broken by a hammer, whose fall is triggered by the emission of a particle from a radioactive substance. Since the emission of the particle is a quantum event, the equations say that in the absence of any measurement, the particle is both emitted and not yet emitted. That means that as long as nobody opens the box to look at the cat, and therefore indirectly measure whether the radioactive substance has emitted a particle or not, the cat is both alive and dead. This seemed ridiculous to Schrodinger, but in quantum theory, the ridiculous is entirely normal. That's clear because in 2003, Anthony Leggett won the Nobel Prize in Physics in part for creating analogs of Schrodinger's cat in electrical circuits. They weren't dead and alive, but they did have particles traveling through them in two directions at once. In 2013, it was shown that the equations of quantum theory tell us that particles can be in two moments at once, not just two places, not just traveling through space in two different ways, but existing at two separate times, simultaneously. It's mind-bending stuff, so let's simplify it a little. Essentially, Albert Einstein can walk into a room and see a message that Isaac Newton has left for him. He erases the message, then writes a reply. As Einstein finishes, Newton comes into the room to write the original message. It's a superposition of Einstein was in the room before Newton, and Newton was in the room before Einstein. It is impossible, as with relativity, to say who came into the room first. The result relies on an additional quantum weirdness, the uncertainty principle, which says it is impossible to extract an unlimited amount of information from a quantum system. That means there's a limit to the precision of any measurement, including a measurement of time. There are, right there in the bowels of our most successful theory of physics, limits to what we can say about anything to do with time. Why? Almost certainly because time isn't a fundamental part of the universe.